Hello, everyone. So I'm Yuji Chinone at the University of Tokyo. And today I'd like to talk about the polar bear and Simon's array. So first of all, I'd like to thank the organizer for giving me such a great opportunity to talk this polar bear and our polar bear and the Simon's arrays business. So okay, I am starting my talk, and so this shows that we are asked to answer this kind of question. Then I hope that I can answer the most of the question in this talk. So please check it carefully. But anyway, so probably people may ask me, so what is the polar bear first? Oh, okay. What is the polar bear? So you guys know what is a polar bear. So then may think CMB is the CMB experiment at North Pole because the polar bear usually live in the South Pole. But of course it's not. And also people wonder what is the Simon's array. So, oh yeah, people say, yes, I know it. Isn't the Simon's observatory? Then the answer is it's not. So Simon's array and the Simon's observatory is different, but somehow linked together. But anyway, so in this talk, I will explain the polar bear and the Simon's array, and mainly polar bear in the context of the data analysis. So this shows the polar bear in Chile. So we have deployed our instrument polar bear in 2011, and we have started our science observation 2012 at the Atacama Desert in Chile. By the way, the altitude is 5,000 meters, and we measure the CMB sky at 150 gigahertz. So by the way, so polar bear is read by Adrian Lee at the UC Berkeley. And you may know that the bear is the mascot of the UC Berkeley. And we really want to measure the CMB polarization sky, B mode polarization sky. Then we named our experiment polar bear. Then I was at the UC Berkeley from the 2011 and 2019. Then I really worked on the data analysis of the polar bear there. Then so that the talk, the business I explain here most comes from mine and our collaborators' business during that period. And Simon's array is an upgrade experiment from polar bear. So we have 3 telescopes, one from polar bear, and each telescope has a 6 times more detector. That's a result in the almost 20 times better sensitivity than polar bear in power spectra. So it's being deployed in 2019, 20, and 21st now. So this is a brand new experiment, and I think this conference mainly somehow focus on data challenge and the data analysis. Then here I will focus on the lensing and the information survey taken by polar bear for the last almost 10 years. So here shows what's unique about the polar bear. So polar bear observed the 3 small patches shown here, like a pretty small patches for lensing between 2012 to the 2014. Then we have reported first season result showing the world first BB auto spectra measurement on 2014. So just a reminder, this is before the bisect2 the announcement. And we have also reported full season result on 2017. this is the lensing measurement. Then after that measurement, we move to the inflation measurement and observe the bicep patch between 2014 and 16. Then we have published an intermediate performance paper on 2017 and published the first result on 2020. You can see that the three power spectra in right figure, which covering the low L of 50 to L of 2000 or something. So this is a unique stuff of the polar bear. Then this shows the list of the polar bear's cosmological publication. I believe they are great, but in this conference, I will not explain each paper, but I will talk about the achievement or the challenge of the degree scale measurement and sub-degree scale measurement by polar bear, measurement and the data analysis by polar bear. So again, so polar bear can have measured its degree scale for inflation and sub-degree scale for lensing. So to do that, we performed a pair difference for sub-degree scale measurement, and we also performed a half-wave plate demonstration for degree scale measurement. So based on this observation and measurement, so polar bear can have published the result in a few years with optical performance and optimal performance and comprehensive systematic budget. So people wonder that is there any challenge to accomplish that achievement? Then so here I will I will explain the several example of the polar bear's challenge of the data analysis. Okay, people may wonder that the processing the huge volume of data is challenging, but it's not for polar bear. So the size of the raw data volume of the polar bear is just as large as all the 10 terabyte. And even the simulation is just as large as all the 100 terabyte. So it's not so huge. Then just running the processing this volume of data is not so challenging. For example, we have a 200 kilo core hours per month in Japan and the US from the based on the KEK computer resource KEK computer center and the NASC supercomputer center in US. So we just use a few percent or a few sub% of the whole resources, and processing this data, this volume of the data is not so challenging. So what's really challenging is this is a general statement somehow. So to investigate any systematic budget with real data, as well as to achieve the optimal sensitivity with measureless data. So without looking at any non-null cosmological input in a timely manner, this is challenging for the, I think, usual experiment in these days. Of course, at the beginning of the observation and the data analysis, we didn't know what's a real instrument model and the data quality, and we didn't know what's the most optimal data analysis. So even if we had tested instrument quite well at the laboratory, or even if we tested, or even if we simulated the pipeline or data analysis quite well without the data, so it's not that enough for analyzing the real data. So real data really tell us the most important things. So we have in polar bear, we have been updated our knowledge with data, like data modeling, the priors, probably I can say the hyperparameter, and iteratively with data again, and until we could achieve the optimal result. I think just that this is kind of data-driven science or data-driven engineering. Then, yeah, I will really show the 6 example of the polar bear challenge and the achievement of the data analysis. So first example is a low frequency noise characterization. So all the experiments cannot escape from the 1/f noise, so it's critical. I believe even a satellite that they cannot escape, then they must suffer from one-over noise. For example, especially the instrument. So right bottom figure shows the PSD from the polar bear with half-wave plate measurement, but without the demodulation. You can see the intensity, the power spectra, whose knee frequency is around a few hertz or something. So of course, this cannot with this PSD we cannot measure any inflational signal. So then we have installed the half-wave plate to perform the good one-over noise. So polar bear has demonstrated a great one-over noise the suppression with half-wave plate. So we have modeled the encoder, timing, jitter, and the packet drop of the timestamp or something like that. And also we have subtracted the half-wave plate synchronous signal. And also we subtracted I2P leakage with the PCA analysis. So that comes from the detector nonlinearity and the instrument polarization. So in the figure, you can see the order 100,000 suppression with half-wave plate here, and extra order 10 suppression with leakage subtraction. So that's resulted in the great performance of the white noise down to the scan frequency as low as 10 millihertz. So that's correspond to the L of 30. So finally, yeah, based on this knowledge, we have concluded the naive filter beam map making is optimal for polar bear map making. And as you know, that this is quite a computationally efficient map making. So example number 2 is noise modeling and robust simulation. So I show the PSD again, but it's different from the previous one. This is the noise PSD for the lensing measurement. I mean, that means without the half-wave plate demodulation, just the pair diff, polarization TOD and the PSD. Anyway, so for this case, noise is white enough L of 500 to 1500. I'm not talking about the order 10 or 100, just the 500 to the 1500. So we are sure that this frequency range, the noise is really white because this frequency science band is really far from the one-over noise residual. Then we run the TOD to map simulation with simple white noise assumption to estimate the error bar on the power spectra. Then it works well, then it has been validated with Null test. So this is a case of the lensing. And again, so we should think about the noise for inflation. So I already says that with the half-wave plate, the demodulation, it's really white, but down to L of 30. But we are worried about, or we are wondering, is the lowest of Elvin, like L from 30 to 50 or something, is really white? And how can we model the realistic one-over noise with this data? Like shape of the one-over noise and the correlation structure over the focal plane and the correlation on the sky and so on. So we make a somehow complicated the data model as well as some algorithm to generate the noise. But we just adapt the sign flip noise technique. So we run the sign flip noise simulation to take the realistic one-over noise property into account at the lowest Elvin. So the first is the sign flip noise realization. So we just, when to generate the realization, so the noise are generated by randomly assigning the +1 or -1 factor to each observation during the coalition. So since the signal is common, then the remaining the map just contain the noise. then we can use that the realization in the in power spectra error bar estimation. This is really nice because this has several advantages compared to the TOD simulation. So we don't need any complicated data the noise modeling, and real noise property. This is real data, so real noise property are taken into account automatically, and it's fast and computationally efficient. So third example is the cross correlation to avoid the noise bias. So usually we take an observation, and for example, first day, second day, third day, blah, 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 100th day or something, or first week or second week, first year, second year. So if we fully coordinate map together, so we suffer from noise bias subtraction in power spectra estimation. But so we haven't fully coordinated maps. We just take a cross correlation among the map that's result in no bias, no noise bias. So this is really nice because it's insensitive to noise modeling as well as robust. It's robust to the unknown systematics. So this is number 3, and number 4 is somehow large, and many people are familiar with this. So Null test, and I will show the challenge and the achievement of the polar bears Null test with the one particular interesting example. So in the Null test, we split the data into 2 and take a difference. So if there is any systematics, the resulting null map has really no signal. But if there is no signal, no systematic signal, we will see the null power. So for this case, we split the data into high elevation data set and low elevation data set, and we see something. Okay, this is a situation of the setup. So this shows this during that period, telescope look at the low elevation, and this time telescope look at the high elevation, and let's take the difference. Then we found a contamination between 2 data sets. So of course, people wonder where that signal comes from. So you can see clearly, so there is no radio source in front of the telescope, but some source is behind the telescope. So does this mean, so yeah, it must be behind, and if the telescope has a backdrop, right, like a far-sidelobe or kind of the sidelobe, so this could see the amount total. This is really behind the bore site. Then this and this really explain the contamination of the Null test. Okay, now we have a theory, and we think we must mitigate it, of course, because it could bias our result. So we introduced the ground template subtraction to mitigate it, and but we must validate it carefully, like which is one of the challenge of the systematic mitigation. First of all, we have measured this backdrop by scanning the sun, with making the map relative to the sun, the position, so-called the sun-centered map. You can see right colorful figure, and in this figure, the center corresponds to the bore site, and around this, you can see some colorful points which correspond to the side lobe. By the way, unfortunately, I will not be able to show the polar bear side lobe map, but this comes from quiet. But anyway, so polar bear measured its side lobe with this kind of measurement. So then we simulated the full CMB observation to reproduce the contamination by backrobe scanning the ground. We now have the theory, the measured backrobe, And then this is the kind of the dedicated simulation done in the polar bear. Then I say this is example number 3 here, the simulation, systematic simulation for the systematic error budget. So we have successfully reproduced this contamination in simulated null spectral map. The right figure shows the real simulated signal, non-null spectra, but you can see the contamination. So this is pretty efficient simulation because 4-pi convolution is not needed. We have measured a real, like a real side lobe that in where most of the power comes from. So we can convert 4-pi beam, but it's somehow overkill to estimate the contamination. Okay, so then finally we have demonstrated the ground template subtraction can mitigate it in simulation, as well as we have demonstrated in the null spectra. You can see right bottom figure. Then concluded we validate the mitigation. We have mitigated the contamination without looking at any non-null power spectrum. So yeah, judging from based on this experience, I believe and many CMB people in CMB field think null tests are really powerful to validate data and analysis. I think we can say this is the data-driven science, and yeah, this kind of the null test is really powerful because we can make an active feedback to the instrument. So we found a problem with the null test, and we have theory, and we have validated it. So now we can propose to install the new instrument. So we developed the visor and the baffle to the telescope, and we finally installed that. This is somehow kind of data-driven engineering also. Okay, the last example is the two pipeline, at least for lensing in polar bear. So we have two independent pipeline to process the cosmological data analysis. So one has filter beam map making, and the other has the unbiased map making feature. And other feature is the flat sky versus hill peaks and the different pixelization and so on. Anyway, so we have developed independent pipeline and process the data independently, then check the consistency. Then we found, we demonstrated consistency of the two pipeline blindly. Then this could tell us the robustness of our data analysis and the data process, data pipeline and the data analysis. Okay, I showed a 6th example, and let's summarize the polar bear's uniqueness and the challenge of the data analysis and achievement. Then move to some brief explanation of the Simon's array status. Okay, polar bear measured its degree and sub-degree scale, and polar bear published the result in a few years with optimal performance and comprehensive systematic budget. So to achieve that, so polar bear has been updating our knowledge, data modeling prior hyperparameter iteratively with data. And there shows a 6 example of the challenging and achievement. So low frequency noise characterization, noise modeling, and robust simulation, cross correlation, Null test, and the dedicated simulation, and two pipeline. I hope the polar bear continue to publish the result in a few years. And to end my polar bear's talk, I will just mention that data release. So our power spectra has been public on Lambda as normal. And the ultimate goal of the polar bear is to advance new experiment, Simon's array and Simon's observatory. We have now many heritage, expertise, and experience. So now move to the next experiments. So we are advancing new experiments. One is Simon's array, which could have a 20 times better sensitivity. And one is a Simon's observatory. I'm sure Emmanuel will give a talk on Simon's observatory, then I will just focus on the Simon's array in this talk. I think I will finish my talk in 2 minutes. So yeah, Simon's array is in field. Then the first receiver, aka the polar bear 2A. So those data are arriving from the field. We are analyzing that. And critical component of the Simon's array is half-wave plate, and especially the first receiver has a warm half-wave plate. So we are taking the data with some calibration campaign or hardware characterization and so on. And I just mentioned, of course, we are developing the pipeline. And last slide shows the status of the Simon's array pipeline. So we are building our pipeline, making it compatible with Toast framework. People may know, but so the Toast framework is the so-called time-ordered astrophysical scalable tools, which is mainly developed NERSC at LBNL. So it's really useful, and Simon's array and the Simon's observatory maintain the compatibility both between both using Toast. Of course, we have developed the component independent from the tools, like the calibration, TOD processing, data quality business, and we are adapting the many heritage from Polar Bear pipeline and Quiet Apps data quality servers. Of course, we are really working on the systematic study with real data. For example, scan synchronous signal investigation and betting the half-wave plate performance, including the I2P leakage. And for the data analysis, we are working on the mitigation of the E2B leakage due to the filter in TOD. So that's it from me. Then I just say stay tuned for the Simon's array. That's it.